All right, welcome to this tutorial on imaginary and complex numbers. So I wanted to take a moment to just set the table for you here. Imaginary numbers are one of the things that are probably the most poorly taught in school. My own experience with this began when I was 14 years old, and my teacher, very well-meaning, taught us the basic rules for imaginary and complex numbers, and we were required to do a few problems with them, and then we moved on. As I look back on that, teaching math, I see that a tremendous disservice was done, because without understanding what these things are and how they're working on an intuitive level, you'll just be completely lost. So I really worry that there are a majority, or perhaps even a super majority of people who are out there taking math classes with zero idea of what is actually going on with these imaginary complex numbers. Now, the good news is that as bad of a teacher as I am, and as poorly organized as these notes might appear, this tutorial will do a better job of preparing you to understand complex and imaginary numbers than if you were just to learn the rules like 90% of math classes. So stick with this, focus, and you will understand. Okay? So let's dive in with an introduction to imaginary and complex numbers. I should preface this by saying that all of these notes that you're going to see here in this video are available both in OneNote file format, so you can actually zoom in and out and edit and take your own notes in these notes. They're also going to be available in PDF form. Just check the description or the pinned comment. These files will also be made available through ogmath.com. That is ogmath.com. Just scroll down. Okay, so section 1, Introduction to Imaginary and Complex Numbers. So a little history here. Back in the 16th century, mathematicians did not have any concept of imaginary numbers. There was a need for them that came up in surveying and in architecture, but people were very skeptical at the time. Even mathematicians were extremely skeptical that these things actually existed, since up until that time, mathematics only recognized positive numbers. And so even the concept of a negative number, forget about an imaginary number or a mixture of imaginary and real numbers, they were having trouble understanding the concept of a negative number. So I want you to know that if you struggle to understand this, right up until about 400 to 500 years ago, nobody understood it. So let's go through the problem that they faced in the 16th century, and we'll see why it is a problem, and we'll see how imaginary numbers solve that problem. So I've got a little problem here boxed in red, and that problem says solve x squared equals -1. Okay, and I say here, read the little sidebar below before continuing. So let's table that for a moment. Now, we know what to do with x squared equals 1. We would take the square root of both sides to get x by itself, right? So here it is, take the square root of both sides to get x by itself. So taking the square root of x squared gives you x, and x equals plus or minus the square root of 1. Okay? the square root of 1 is understood to be 1 only because allowing the negative solution would violate the vertical line test. Thus, the square root would not be a function. So for mathematics, when we take the square root of a number, for functional purposes, we're only considering the positive root. Remember, functions must only have one output. So for any given x, there can only be one outputted y value. That's why we only take the positive root when we're working with functions. Now, so we know that this works. We can do this. X squared equals 1, positive 1. We know we can solve that for x, and restricting to the positive solution, it's even functional. Now let's try to apply that same process to x squared equals, okay, and here's the big thing, x squared equals negative 1, okay? X squared equals negative 1, not positive 1. Okay, so first we take the square root of both sides, just like we did before, and then we get x equals plus or minus the square root of negative 1. And here, guys, it's like the train grinding to a halt on the tracks. I say here math.exe has stopped working. You know, in the words of Tom Hanks from Apollo 13, Houston, we have a problem. Okay? So what is wrong here is that 1 times 1 equals 1, but negative 1 times negative 1 also equals 1. Okay? So we have a problem here because we're trying to take the square root of a negative number, but we're finding out that if we were to follow our process of thinking about what a squared number is, think about it like this, negative 1 squared, okay, should equal positive 1, okay? Negative 1 times negative 1 equals positive 1. That's a problem because when we're taking the square root of a negative number, what we're supposing is that you could do the other thing. Like, I'll give you an example. The square root of 64 is understood to be plus or minus 8. Okay? And if you were just restricting to the positive solution, the square root of 64 would be 8. Okay? Now, what that implies is that 8 times 8 equals 64. So this is the problem, okay? So let's do this again. We have x squared equals negative 1. We take the square root of both sides, and we get x equals plus or minus the square root of negative 1. So let's just restrict to the positive solution. X equals square root of negative 1. So what we would have to suppose is that whatever that is, okay, when you multiplied it back together, you would get a negative number. But that doesn't happen. Okay, so anything times itself is going to be positive. A negative times a negative is always going to be a positive number. So we have a problem. Okay, that was the problem facing mathematicians back in the 15 and 1600s. Okay, I've got to stop touching that screen. So recall that we can think of the principal solution of the square root of x as any number that can be multiplied back together to give the original x, like how the square root of 49 equals 7, and conversely, 7 times 7 equals 49. So this was the big problem right here. But the square root of negative 1 equals 1 doesn't work because 1 times 1 equals 1, not negative 1. And the square root of negative 1 equals negative 1 doesn't work because negative 1 times negative 1 equals 1, not negative 1. So you see the problem? They had to come up with something for the square root of negative 1. This was the genesis of our next section here, the imaginary number I. Okay? Give me just a moment. Okay, so let me zoom in on this for a second. Mathematicians gave the name imaginary to this number I, okay, because they were so skeptical that the idea of the square root of a negative number would exist, that they called it imaginary. Okay, but here's the deal. Over time, we in mathematics and just humans in general figured out that these are real numbers. Okay, so they're not part of the set of real numbers, but they are as tangible and useful, and they exist as much as any other number. 1, 2, 3, 4, okay, are as real, in air quotes here, as I. Okay, so we're gonna wade our way into the pool here, and I promise that there's some really cool stuff up ahead that's gonna make this seem, all this hand waving here at the beginning is gonna seem silly because stuff is easy once you understand what's going on. Okay, so mathematicians called the principal root, remember that's the positive root. Okay, just read this as positive root of the square root of negative 1 as the imaginary number I. Okay, so that's the key. The benefit of doing this is that our original big problem has been fixed. So let's go through these three little exercises here. Here's the first one. Oops. Here is the first one. Just as 7 squared equals 49, I squared equals negative 1. So what does that look like? What that means is I times I equals negative 1. And that means, that means I squared equals negative 1. Which means if I wanted to solve for I could take the square root of both sides, and I'd have I equals the square root of negative 1. Bingo. So this is the solution to our situation that we were facing up here. Okay? And this, we just replaced x with I. All right? So let me erase this and let's continue. Just as the square root of 49 equals 7, the square root of negative 1 equals I. Okay? So that's the second thing. And then 3, just as 7 times 7 equals 49, I times I equals negative 1. All right, we just went over that again. So math.exe now works again. That's great. Okay. So, little sidebar here that is really important. Okay, let's read this together. It is very important to understand that imaginary numbers, guys, this is so key. I'm going to highlight it here for you. Imaginary numbers actually exist. Now, it is very understandable that you are worried and confused. Okay? You are reacting to imaginary numbers the same way people in the 1600s reacted to negative numbers. They did not believe in them, ladies and gentlemen. This is what someone from the 1600s might say to you. If you have 4 cows and subtract 5 cows, am I supposed to believe you now have a negative cow? Because that sounds ridiculous, right? Well, here's the thing. That's exactly what we mean, right? But back then, they had no concept that there could be like this negative value, okay? So I come up with a better way to explain negative numbers to a farmer in the 1600s. Now, why are we talking about negative numbers? Because in the same way that they were confused about negative numbers, which we now take for granted, we are confused about imaginary numbers, which we assume in 200 years the children in first grade will be working with them. Okay? They just haven't quite assimilated into our culture. So, a better way to explain the concept of negative numbers to a farmer in the 1600s is to talk about something we all know a lot about and have a kind of instant familiarity with, and that's money. So here's you, okay, you the viewer, talking to the person in the 1600s. If you had $4 in your bank account, but you wrote a $5 check, you'd be overdrawn by $1. So one easy way of saying that is to say that you have a bank balance of negative $1. Makes sense. If you have $4 in your bank account, you go to the store, okay, and you buy some groceries at Berkshire's or Walmart, and you write a check, and those groceries cost $5 or $6 or $10, and Walmart deposits that check, then your bank is going to put an overdraft on your account because you've gone into the negative balance. So we have an understanding of negative numbers just with our money. Okay, so the farmer from the 1600s, that was appealing. Oh, I get it now. Thanks. And you say, no problem. So now that we've got a bit of a grasp on what farmers in the 1600s thought about negative numbers, let's get back to our original problem. Okay, so here's our original problem. X squared equals negative 1. All right. Would you agree with me that another way to say x squared equals negative 1 is, and then here's the thing, what number multiplied by itself equals negative 1? Okay, what number multiplied by itself equals negative 1? So we can write x squared equals negative 1 as x times x equals negative 1, or even 1 times x equals negative 1. So let's think about a way to say 1 times x equals 9. The question here is, what transformation, when applied twice, because there's 2 x's, turns 1 into 9? Okay, this is like turning straw into gold. How do we turn 1 into 9? So here's the cool explanation. Take the 1 and scale it up by 3 times twice, and you can transform the 1 into a 9. Now, this language, when I'm just talking to you, it sounds a little bit confusing. So here's what we mean. I drew a little diagram for you. Take the 1, scale it up by 3, right? What scale it up by 3 means is multiply by x. Okay? Scale it up by 3 means multiply by x. And then you take whatever that is, 1 times 3, and then you multiply it by 3 again. Scale it up by 3 again. So you have this process where you start with 1, okay? You multiply 1 times 3. Okay, where are we at now? So right now we're at 3. And then you take that 3 and you multiply it times 3, and now you have 9. We can play the same game with literally any equation. So if we really can do it with an equation, let's do one that looks kind of hard. So again, here we're assuming that x is 3. So for the purposes of this, we're going to assume that x equals 3. So what we're going to start with is, and we'll see if x equals 3 works. So here, 2 times x to the 4th power equals 162. So we're going to rewrite that. Instead of saying 2x to the 4th, we're going to say 1 times 2 times x times x times x times x equals 162. So I've got the steps written out here. You start with the 1. You scale the 1 up by 2. That means multiply by 2. So 1 times 2 is 2. Now you bring that 2 over here. Now scale 2 up by 3 because we're assuming that x equals 3. So we scale 2 up by 3. 2 times 3 is 6. Fair enough. Now put the 6 in, okay? We're going to do it again and again and again. So now scale 6 up by 3. Well, then it's 18. Now plug the 18 in. What's 18 times 3? 54. Plug the 54 in. 54 times 3, 162. So that's how we got from 2x to the 4th to 162. What we were doing is we took 1 and we turned it into 162. That's what we just did, okay? That's what we just did. So if we were showing it algebraically, this is how you would have done it. You wouldn't be thinking about the 1. This is the old way that you did it before. Okay? So hopefully you have like a new understanding of how to read when you see something like 2x to the 4th equals 162. The big takeaway from this section is start with 1. Okay, start with 1 and then do all the things that's going to happen. So you started with 1 and then you follow the instructions. You multiply by 2 and then you multiplied by what we know x is 3. Okay, and you do this little process and then it equals 162. That's the big takeaway here. Okay, so let's go down. We're going to now apply the very same logic to x squared equals -1. So this is the same logic that we just dealt with. All right. X squared equals -1. But instead of saying scale up, we say, this is the point where I want you to listen very closely. Rotate counterclockwise by 90 degrees. This is the really big idea, okay? This is the really big idea. And up until this point, that all of my blabbering on, it just may have been confusing. You're about to see a visual that's going to make all of this seem really cool. So here it comes. This is the part where you're going to learn what imaginary numbers really are. So x squared equals -1 means 1 times x equals -1. Again, we're traveling from 1 to -1. What is happening in between? Well, in this case, we know that x equals I. Remember, the square root of -1 equals I, right? So that's how we know that x equals I. So now forget about x from now on. We're just going to be talking about I. We take the 1 and we rotate counterclockwise. I'm abbreviating CC here. Rotate counterclockwise by 90 degrees. That is what happens when you multiply by I. So here's what's happening. We are taking 1 and we are multiplying by the imaginary number I. Here I want to use this cool font or this cool color on the pen. Okay, so we're taking 1 and we're multiplying by I. Okay, and what that means when we say multiply by I, multiply now takes on a new meaning. In imaginary numbers, multiply means rotate 90 degrees counterclockwise. Okay? That's what multiply means. So we start here at 1 and we rotate counterclockwise 90 degrees, and now we're at I. Okay? Now we're trying to get to -1. So we have to do it again. Now we're going to do it again. We're going to multiply by I again. Now, let's move down here. Take the I, because now you're at I, and rotate counterclockwise by 90 degrees again. That is, multiply by I. So here we're starting at I now. We're going to -I. So now we're at -1. So you see, as we move around this circle, traveling in 90-degree increments, we start from at 1 and we multiply by I. So 1 times I is I, obviously. 1 times any I is I. Now I times I is -1. Okay? -1 times I is -I. -I times I takes us back to -1. So, let's do this. 1 times I equals I. 1 times I equals -1. 1 times I equals -I. And finally, 1 times I equals 1. So we're going 1 times I to the first, 1 times I to the second, or I squared, 1 times I to the third, or I cubed, and 1 times I to the fourth will take me from I to -1 to -I and all the way back to 1. Okay? So that is what imaginary numbers are all about. So we already did this. I bet you know how to solve I cubed equals -I. Just rotate by 90 degrees one more time. I cubed equals -I is 1 times I times I times I equals -I. Now look here. We start at 1. We rotate 90 degrees to the left here, counterclockwise. Now we're at I. We multiply by I again, and that takes us here to -1. And then we multiply by I again, and now we're here at -I. Okay? Now look, I've written it out here in English in orange, and then imaginary math in this multicolored. Here's the orange. Okay? The first step, rotate by 90 degrees, and I should say here counterclockwise, okay? Imaginary math, multiply 1 times I. Now we're going to do it again. Rotate by 90 degrees counterclockwise. In imaginary math, multiply I times I. Okay, so we just learned something, didn't we? We just learned that I times I equals -1. All right? 1 times I equals I. Now here, we're at -1. We're going to multiply by I. -1 times I is -I. Well, that makes sense, right? -1 times anything would just be the negative of that thing. And then finally, negative I times I equals 1. Okay? And the reason that that works is because negative I is equal to I times I times I, or I cubed. Okay? And then you're multiplying that times I. So you're multiplying I cubed times I. You apply the product rule, and you get I to the 3 plus 1, or I to the 4th. So I to the 4th power is 1. All right? I to the 4th power is 1. Okay? So I hope you can see that one final rotation would bring us all the way back to 1. So I to the 4th equals 1. So look here. This is really cool. You can see that this thing just goes round and around. So all we're going to do is start at 1 and just multiply by I forever. So 1 times I is I. Okay. Here we're moving in this direction. What is going on? Okay, here we're moving in this direction. 1 times I is I. Times I is negative 1. Times I is negative I. Times I is 1. Continue. Times I is negative I is, times I is I to the 5th. Okay, so we're going I to the 1st, I to the 2nd, I to the 3rd, I to the 4th, I to the 5th, I to the 6th, I to the 7th, I to the 8th, I to the 9th, I to the 10th, I to the 11th, I to the 12th. It goes on and on, around and around. The I's move in a circle, okay? You know how it is on the coordinate plane where numbers just keep getting bigger and bigger and bigger? Well, the I's, they're just circling around, okay? They're just like spiraling around like this, just getting bigger and bigger, but in a circle. So that rotation thing, the rotation thing is the key. Rotation is the key. This is the huge, big, like, aha moment that when you multiply by I, you rotate 90 degrees to the left. Let's do that right here. When you, let me zoom out. When you multiply by I, you rotate 90 degrees counterclockwise. Okay? So now let's generalize our understanding. I is actually part of a new imaginary dimension. I should have said here, I is in a new imaginary dimension to measure a number. Okay? Look at this. This is the imaginary axis right here. It is perpendicular to the real number axis. So here you have numbers, and here you have letter I's. Okay? And we're to get from 1 to negative 1, you have to pass through the imaginary axis. You see that? So you cannot cut across. This is not allowed. You can't do that. You have to follow the circle. Okay? So to get from 1 to negative 1, you don't subtract 2 in this example. You multiply your way to negative 1 by multiplying 1 times I, and then I times I. So you rotate your way to negative 1. Okay. So we went over this. I is a new imaginary dimension. it is perpendicular to the real number axis. So I, or negative I, is what numbers become when they are rotated. Okay, so this rotated thing is what's happening. Multiplying by I is a 90-degree counterclockwise rotation. Multiplying by negative I is a 90 degrees clockwise rotation. All right? If you start with a real number, you have to rotate 2 times counterclockwise by 90 degrees to get back to the real number line. See, your first multiplication by I takes you into the imaginary plane. And then you multiply by I again, you get out of the imaginary and you get back to the real. Okay? Guys, this is mind-bending stuff. But now we have a new way to answer the question, how do you turn 1 into -1? Okay, so there's 2 answers here. Answer 1, we rotate it counterclockwise by 90 degrees 2 times. That makes sense. So we did that first rotation, right? We got to I, and then we did that second rotation, and we were at -1. All right, here's the life cycle. Just like that. Around and around and around she goes. Now here's the other answer. We multiply it by I squared, because I squared is -1. Remember, I squared equals -1, because the square root of -1 equals I. Right? So by our rule, I times I has to equal -1, so that the square root of -1 could equal I. This is the whole point. So rotate counterclockwise by 90 degrees. Translated, multiply by I. Multiply by I means rotate counterclockwise by 90 degrees on that imaginary, that plane that consisted of the imaginary numbers. Okay, here was I and here was -I, and it was crossed by the real number plane right here. Okay, so this was the real number plane with 1 and -1. Okay, so you rotate your way in this new way of looking at the world. And the way that you rotate is by multiplying by I. Okay, so you can't, the way that you get from 1 to I is by multiplying by I. The way that you get from I to -1 is by multiplying by I. The way that you get from -1 to -I, is by multiplying by I. The way that you get from -I to 1 is by multiplying by I. Okay, so I hope it's starting to click now. All we're doing, so let's look at this. If we start with 1, right, and we multiply by I squared, where should we end up? That's 2 rotations, right? Because that's 1 times I. So we're going to be 180 degrees from where we started. So we go from 1 to I. That's our first 90-degree rotation. And then we go from I to -1. Okay, so you can actually do this with other numbers. So let's say you started with 4, okay? And you wanted to multiply 4 times I cubed. Well, where would you be? You'd start at 4, right? So you'd be further out on this number plane, right? You'd be way out here somewhere to be at 4. Okay, so let's just call 4 is right here, and you'd circle way up here to be at 4I, and then you'd circle way over here to be at -4 back on the real number line, because -4, -4 in this example is equal to 4 times I times I. And remember, 4 times I is 4 times I squared, which is another way. Remember, I squared equals -1, so that's 4 times -1, which is -4. So that's how you get from 4 all the way over to -4. Now let's see if I can undo my way out of having written all this mess. Maybe, maybe not. Uh-oh. So we'll see what that does later. Wonder if it's going to erase all that. I think I probably need to sit still for a second. Okay, so that's all. I have to... Let me just erase this. Okay, good. All right. Oh, I never finished the rotation. So we said we were doing 4i cubed. We made it all the way to -1. One more big rotation. Multiply by I again, and we'd be at negative 4i. Okay, because we were here, we were at -4, and then we multiply by I again, and we're at -4i. If we wanted to get back to home base, we would just multiply by I one more time. So -4 times I, okay, that's -4i times I is -4i squared. I squared is -1, so it's -4 times -1. Then we're back to +4, okay? I think if you just do some examples like this, you'll get it. It'll be easier for you to get it if you just do some examples and convince yourself that this actually happens, okay? But it is one of those things where you have to do it. You watching this video, it's not gonna click for you. You've got to stop the video and you have to work your own little examples, okay? Draw a little picture like this and follow the process. You'll get it. And when it clicks for you, you'll say, oh, I understand now. Okay, so that's what I want for you. I want you to have that big aha moment. I'm just trying to, as we go through this, I'm trying to erase what we write so that this is fresh when I teach the next person. Okay, so now we're on to a new section. Numbers, okay? Numbers are now two-dimensional. Yes, ladies and gentlemen, numbers were always two-dimensional, but we just didn't tell you about this when you were younger, right? It's like we didn't want to tell you about this the truth of the matter, because it would have frightened you. For example, we didn't tell you that Santa Claus wasn't real until you were older. We would, tell you the tooth fairy isn't real until you were older, so you would feel a little bit less anxious about the situation. I think it's a mistake. I think we should have been showing this rotation business by multiplying by I from the very beginning. Because by the time you get into your teenage years, trying to assimilate this into your understanding is a little bit difficult. Okay, so can numbers be both real and imaginary? Yes. Oh, of course they can be. Who says we have to rotate exactly 90 degrees? If we keep one foot in the real dimension and another foot in the imaginary dimension, it looks like this. Okay, so here's this picture again, just like from up above, right here. But in this picture, we've kind of labeled it a little bit differently. So this axis here that I've done in that cool marker, this is the imaginary axis. And this red line here, this is the real axis. And throughout these notes, I've maintained this where if you see something with this color, red, this means like a real number. And if you see something that is this color, this cool color here, this means imaginary. Now the question is, can we have numbers that consist of both the real, okay, and the imaginary? I should write it with the other one, right? And the imaginary. Right? Yes, we can have that. So we can have combinations of real and imaginary numbers. And when you combine these together, all right, when you combine them together, I use this color to combine them together, this purple color here, because it's kind of like a blend of these two. When you combine real and imaginary numbers together, they're called complex. All right, so let's see what this is all about. So here, I want to combine together I and 1. So we just add them together, guys. See, 1 coming from right here plus I coming from right here. So look, instead of rotating the full 90 degrees, which would bring me up here to I'm just going to rotate halfway, exactly halfway, and I've rotated 45 degrees from the real axis into the complex into the imaginary axis. I've rotated halfway there. I'm kind of in the in-between, right? In the upside down world, so to speak. So let's zoom in on this stuff over here on the right. Notice that at 1 plus I, we are at a 45-degree angle with equal parts real and imaginary. This 45 degrees right here, this is called the angle of rotation. Okay, this is the angle of rotation. This right here. The angle of rotation is 45 degrees. Now, we're going to learn another name for it later, but right now, it's just 45 degrees. Okay, right now it's the angle of rotation. So 1 plus I is called a complex number because it has both real and imaginary parts in the form A plus BI. Okay, where A is the real part and B is the imaginary part. So in this example, A equals 1 and B equals 1. So it's just 1 plus 1I. So I think this is important. I want to zoom down here for just a minute and show you something. You see this? This is the imaginary and real axis together. This is called a complex plane. So you know how we plot coordinates x comma y? Well, here we're plotting coordinates real comma imaginary. Okay, so this is the real number, and we used to call this x, and this is the imaginary number, and we used to call that y. Okay? So if I wanted to express this coordinate in imaginary notation, I would just say 3 plus 4i. Okay, let's try another one. How about right here? Well, you see, it would just be 5 plus 1i, or 5 plus I. Now you try this one over here. What's the real portion of it? Write that in red. The real portion is -8, right? You just look down here and you see that the real portion is -8. What's the imaginary portion? All right, well, go over there and look for it, and you see it is 6i. Okay, so your complex, kind of your mixed number here, your complex number is -8 plus 6i. Okay, -8 plus 6i. That's how you work with this. So that's what complex numbers are. So just to look at some others, look over here. So what would this be? Right away you're seeing it, aren't you? Negative 4 plus negative 4i. I guess we can simplify that, huh? Negative 4 minus 4i. So kind of like the coordinates of that point are negative 4 comma negative 4i, right? If you wanted to plot the coordinates of that point. So it works, guys. It works exactly like the coordinate plane that you've grown to know and love, right? Just one more here I want to do. So that one, where are we at? So on the real axis, we're at 8. On the imaginary axis, we're at 2i. So 8 comma 2i, or 8 plus 2i. Okay. So let's get back to our notes. I think this was useful, and I mean, I actually jumped ahead a little bit because it seemed important that we do so. Okay. Now let's dive back into this. So we were rotating our way into the complex plane here, into the imaginary axis a little bit, halfway there, and we have formed a triangle. Do you see that? So if we draw a line from the origin out to the point of rotation, right there, we have formed a triangle in here. See that? There's your triangle right there. And so if you're thinking about triangles, a lot of stuff should be coming to mind. But the main thing that should be coming to mind is the Pythagorean theorem. All right? The Pythagorean theorem is going to be important for us here in a minute. So let's take a closer look at that triangle. So this is just exactly the same thing you just saw, but with that triangle filled in. And then I've labeled this the A component, okay? Because remember, a complex number is written in the form A plus BI, right? Here's the A part. This is the real part. Okay, here's the B part. This is the imaginary part. Or I guess I should try to keep consistent with that color usage. The B goes with the imaginary. Okay, and the red goes with the real. Do you see how that number is put together? So, here is the question. How big is an imaginary number? Or I even have it down here. What is the magnitude of the imaginary number? So, this is just another way of asking, what is the hypotenuse length of that triangle? Okay, you see this? Now, what I'm asking you is, what is this hypotenuse length right here? Now, that's where that Pythagorean theorem would come into play, wouldn't it? Because we can say that c squared equals a squared plus b squared. So a plus bi, that is c, right? The hypotenuse, here, or right out here, the hypotenuse equals the square root of a squared plus b squared. You've been solving those problems since you were little, okay? So that's how we find out the hypotenuse. We take the square root of the sum of the squares of the other two sides of that right triangle. And I should note here, I should have noted, this is a right triangle right here, okay? So a squared plus b squared equals c squared. Okay. Now we're going to look at a real example here in a moment. All right. So now we're going to move on to a real example. Now in this real example, just remember that multiplying by a complex number just rotates by its angle. I hope at this point we understand that multiplying by a complex number just implies that there's a rotation happening. Okay, see that? So here's our example. Taylor is on a boat sailing 3 miles east for every 4 miles north. So she's in a boat and she's heading in this kind of northeast direction here, okay? She's heading in this direction in her boat. She wants to change her heading by 45 degrees counterclockwise. Okay, so she wants to turn the boat 45 degrees counterclockwise. What is her new heading? All right, so she's going to turn the boat 45 degrees to this direction, and we want to know what her new heading is after that. Okay, so we don't know this. We don't know this, but that doesn't matter. We're not even going to find that. We don't care about that. So we're going to be able to find her new heading, though. Watch this. So let's zoom in on this a little bit. Taylor's original heading can be written, okay, remember, she's sailing 3 miles east for every 4 miles north. 3 miles east is the real portion. 4 miles north is the imaginary portion. And remember, we can just add those, right? So down here on the complex plane, here's what Taylor's doing right now. She's going 3 miles east for every 4 miles north, right? That's what she's doing. So her current situation is 3 plus 4i. Okay? Let's go back to the problem here. Okay, so we can write this as 3 plus 4i. That's 3 east, 4 north. Okay, east and north. And she wants to rotate counterclockwise by 45 degrees. Remember, she wanted to change her heading by 45 degrees counterclockwise. Okay? So, well, let's start here. 45 degrees is 1 plus I, a perfect diagonal. Okay? So we can multiply 3 plus 4i times 1 plus I to find her new heading. And remember, all that multiply means is rotate. Multiply means rotate. So what we'll use is FOIL to find the product of these two complex numbers, 3 plus 4i times 1 plus I. So we multiply the first, outer, inner, and last. That's what FOIL means. FOIL means first, outer, inner, last. So let's do this together. The first two numbers, 3 times 1. Okay, that's just 3. Outer, 3 times I. Well, that's just 3i. Inner, 4i times 1. Well, that's just 4i. And then last, 4i times I is 4i squared. Okay, so the next thing in the process is to combine like terms. Okay, we're going to combine like terms. So here we're going to combine the 3i and the 4i together to give 7i. Okay, so you just add those coefficients. The 3 just comes down, so you have 3 plus 7i plus, and remember 4i squared. Remember that I squared equals negative 1, so that's really 4, not times I squared anymore, but 4 times negative 1. So let's move down to the next step. The 3 just comes down, that's 3. The 7i comes down, that's 7i. And now 4 times negative 1 is negative 4. Combine these two real terms here. 3 plus negative 4 is negative 1. Okay, so negative 1 plus 7i. So remember what that means in the context of this problem. That's negative 1 miles east for every 7 miles north. Okay, so negative 1 mile east for every 7 miles north. Now we can see what Taylor's new heading is. She's moving negative 1 mile east. Give the computer a second here to catch up with us. It'll pop up. Okay. Hopefully it'll pop up. Okay, so now it's back. So we have this new complex number here, negative 1 plus 7i. So Taylor's new heading is 1 mile west, which is the same thing as negative 1 mile east. You know, if you're confused about that, you've got north, south, east, and west. So the concept of negative east is just west. All right, so her new heading is negative 1 mile east, which is the same thing as saying 1 mile west, for every 7 miles north, negative 1 plus 7i. So this is taking that complex plane and putting a real world example. Now this is where I wrote this big wow. The fact that we can do this without using trigonometry or a calculator is just crazy. Now this is the cool thought right here. All we really need to know is the complex form of any angle, and we can play this game all day. So one question to think about is, how do we work out the angle of rotation for any given complex number? Okay. So of course that's the next thing we're going to talk about, how to find the angle of rotation of complex numbers. That is our next section. Okay, so we're going to take just a little break here and then we'll talk about that. Okay. So, section 2 here. How to find the angle of rotation of complex numbers. Now, for this, we're going to be using something called the Argand diagram. And that might not be the correct pronunciation, but it's the Argand diagram. Remember this picture from our last lesson or the last section? This is that same picture that we drew earlier, that we had the imaginary axis going up and down, and that's where the imaginary numbers lived, and then we have the real axis here, and we rotate our way through it by multiplying by I. Okay, we don't cross through, we rotate around by multiplying by I. So let's go over this. This graph with the imaginary axis plotted vertically, just like the y-axis, and the real axis plotted horizontally, just like the x-axis, is called an Argand diagram. I wanted to talk about this historically. It's named after a mathematician from Switzerland, Geneva, Switzerland, named Robert Argand. He lived from 1768 to 1822. He was entirely self-taught, which is just incredible, while managing a bookstore. We should also note here that a Norwegian mathematician named Caspar Wessel discovered it first. So Caspar doesn't get top billing. He didn't get his name on the thing. That happens a lot. You know, we always say Isaac Newton invented calculus or discovered calculus, but actually a guy named Leibniz found it before him. But Newton gets the gold medal because I guess he had a better publicist. So, a little note here in blue: Argand diagrams aren't required to show the circle and can extend into infinity on both axes. We already saw the diagram below. We're actually aware of how to do this now. Here's the diagram, the Argand diagram for 4 plus 8i. So there again, we plot a point, and that point has both a real coordinate and an imaginary coordinate. So it's like 4, 8. But we write that in complex notation as 4 plus 8i. So I even say here, remember it's a, the standard form is a plus bi, a plus bi. Okay, so here the 4 is the a, and the 8 is the b. Okay? So notice that nothing is happening strange on this imaginary axis. It's just the numbers, just like if it was y, but you put an I after them. So 1i, 2i, 3i, and the same thing on the negative side. The real axis looks exactly like it always has. Okay? So we're going to do something with this. Remember, we're talking about this angle of rotation. We can connect our origin here to the green dot using a line. We actually call this line a vector. Now, the reason we call it a vector is because it has both a magnitude and a direction. Now, when we're talking about complex mathematics here, imaginary numbers and real numbers, we call the hypotenuse here of this triangle, remember, we're going to end up with a triangle, right? We're going to end up with a triangle. We call that hypotenuse, it has a special name, and it's called the modulus. Okay, modulus. The complex modulus. So this angle, which that Greek symbol there is called theta, that it just stands in for the angle. We don't know what the angle is, so we're just going to call it theta for now, kind of like x or y or z or m or n. It's just a variable name. We don't know what it is yet, but we reserve that for an angle measurement. The angle theta is called the argument. Okay, so this angle right here, this is called, right here, that angle right there is called the argument. And it doesn't have any special meaning, it's just the angle. That in mathematics, in this mathematics, we call that the argument. And we say argument of z, where z is the complex number. So here, this equals z. 4 plus 8i is z, so we would say arg of z, or arg z, and that's the same thing as saying arg, or the argument, or the angle of 4 plus 8i. Okay? So that's some cool stuff there. So for this example, we are seeking the argument or the angle of rotation of 4 plus 8i. So we're throwing a lot of stuff at you here. The word argument, okay, this word argument is just another way of saying angle of rotation. Okay, it's the same thing as angle of rotation, but we're going to use the proper term here. And instead of saying hypotenuse, or vector, okay, we're not going to use those terms. We're going to say modulus. So just new terms for stuff we have already been working with. Okay, but that's what it is. The hypotenuse, or this green line right here, or this vector, that's called the modulus. This angle of rotation is called the argument. So every complex number has both an argument and a modulus. Let me write that down because you need to know that. All complex numbers have both, say it this way, have both an angle of rotation and a hypotenuse, or an angle of rotation and a vector. All complex numbers have both an argument and a modulus. All right, and that's how you abbreviate those, arg and mod, right? So it's arg z mod z, where z equals a plus bi, which in this case is 4 plus 8i. So these are the features of complex numbers. Basically, they have an angle of rotation, okay, and they have a hypotenuse length, which is also the vector. So we call that argument and modulus. And all complex numbers have these features. Okay. So for this example, we are seeking the angle of rotation for 4 plus 8i, and we're seeking the length of that green line. When I say modulus, what I mean is the length of the green line. So the green line, I want to find that length. Of course, I'm going to be using Pythagorean theorem to do that. That's the easiest thing, so we're going to start with that. Finding the length of the green line, which remember we're calling that length, or that hypotenuse, we're calling that modulus or mod of 4 plus 8i, can be done easily using the Pythagorean theorem. And remember, the Pythagorean theorem says a squared plus b squared equals c squared. Okay, so I've written in here that c just means mod 4 plus 8i. Okay, or the modulus, or the length of that green line, the hypotenuse of that right triangle that we could draw in there, is what we're calling modulus of 4 plus 8i. So we'll start with this. C squared equals a squared plus b squared. All I did was put the c squared over on the left, equals a squared plus b squared. And then I take the square root of both sides, so I get c by itself equal to the square root of a squared plus b squared. This is something that you have done a billion times. So then we substitute in our a values and our b values. Remember here that the 4 is the a value and the 8 is the b value. So we're substituting that in right here. So now we have the square root of 4 squared plus 8 squared. Now if we go ahead and square the stuff underneath the square root symbol, the radical sign, we have c equals square root of 16 plus 64, or c equals square root 80, which can be simplified down to 4 square root 5, or, and this is the more common thing to do, just estimate it in the calculator. Okay, so I went and put square root 80 in the calculator, and I rounded to the hundredths place, and I got 8.94. Okay, so this is what mod of 4 plus 8i equals. It equals approximately 8.94, or exactly 4 square root 5, or exactly square root 80. Okay, those are all the same thing. All right, so this is C, which remember is modulus, the length of that green line, of 4 plus 8i. And remember, that was mod of Z. All right. So I feel like we've got that down. Hopefully my document will pop back up. Must be chewing up some resources on this computer for it to be responding so slowly. Just give it a moment. It'll pop back on. Okay. So we found the modulus. We found the magnitude of that green line. We found the hypotenuse of that right triangle. So let's bring everything into focus here. Now we want to find the angle of rotation. So now we want to find theta, which we originally called the angle of rotation, but now we are calling by its formal name the argument, or arg-z. Okay, and remember that z was 4 plus, this should have said 4 plus 8i. Okay, that was our original complex number that we were working with. Okay, so here we've got a lot to look at here. Give me just a moment. Okay, so in math, when we want to find an angle, but all we know are the lengths of the opposite and adjacent sides. So let me explain what I mean by that. I want to find this angle, but the only information I have available to me is the angle, or the length of the side opposite that angle, and the length of the side adjacent to that angle. Adjacent means kind of right next to it. So I know those two things. Okay. Good. So we already talked about this, but that b value is 8 because it's at 8i. So that coordinate value there is 8. It's like the y distance would be 8. And here the x distance, or the real distance, is 4. All right, so that's what we know. We know the opposite and adjacent side lengths respective to this angle, theta. Okay, this is the angle that when I say we know the opposite side, see, I know the opposite side and I know the adjacent side. Okay? So when we know those two things, the way that we find out what the angle is we do something called taking the arc tangent. This is also called the inverse tangent, represented as tangent to the -1 of the opposite side over the adjacent side. All right, so you don't have to know anything about trigonometry to understand this. Basically, you just plug it in. All right. Now, there will come a time where you'll understand what tangents and sine and cosine and inverse tangent are. All that doesn't matter right now. We're just trying to get some useful information. Okay. On your TI-84 graphing calculator, you'll have to use one to actually calculate this. First, hit the mode button and then change from radians to degrees. By default, your TI graphing calculator is going to be in radians. But if you hit the mode button on that calculator, okay, here's a little picture of one. Hit the mode button there, and then you'll have a menu come up and change radians over to degrees and then hit enter, and then you'll be ready to rock and roll with the inverse tangent. Okay, so the arctan button or the inverse tan button is second, then tan. So here's the second key and here's the tan key. So that's tangent, arc, tangent. Okay, so we're almost there. We are almost there. Okay. Okay, since the side opposite our angle is 8 and the side adjacent to our angle is 4, we want to compute the tangent of the arctangent or the inverse tangent of 8 over 4, opposite over adjacent, and that's 8 divided by 4 is 2. So the arctangent of 2 is going to give us our angle of rotation, or in this case, our argument. So the arctangent of the arctangent of 2 is approximately equal to 63.43 degrees. So our angle of rotation, or our argument, for our complex number 4 plus 8i, that is arg of 4 plus 8i, is approximately equal to 63.43 degrees. Okay, so you did it. That's the finished product. We found both the modulus, which is 4 square root 5, okay, or square root 80, and we also found the angle of rotation, which is the argument. So remember, for 4 plus 8i, its modulus is 4 square root 5. That's the length of that hypotenuse, the green line. And its argument, or its angle of rotation, from the real axis up into the partial, that area in between the imaginary axis and the real axis, that's the complex plane. The angle of rotation there is 63.43 degrees. So we can find this angle for any complex number. We can also find its magnitude, so its modulus. So let's learn about some operations with complex numbers. Well, we're on the downhill slope now. This is section 3. First of all, let's talk about addition and subtraction. To add complex numbers, a plus bi and c plus di, you just add the real values together and the imaginary values together. Okay? Don't mix them up. That's why I've got them all separated by color here. So let's do an example. Add 3 minus 4i and negative 2 plus 6i. So here I've written z equals, and then open parentheses 3 minus 2, because I'm going to subtract, or rather I'm going to add together the real elements of the complex numbers. That would be 3 plus negative 2, so that's 3 minus 2. And then I add in the imaginary elements of the complex number, which are negative 4 and 6. And what I do is I just put I out to the right of those two imaginary numbers. So negative 4 plus 6, I. So our final z is 1 plus 2i. Okay. So what I did is I went ahead and found the modulus and the argument of that without even touching a graph. I just plugged it into the calculator. So remember, for the modulus, I would just be noticing here that 1 plus 2i plotted on the complex plane here. That would be 1 plus 2i would be right here. 1 plus 2i, that would be right there, right? And that would be 1 comma 2, or 1 plus 2i. Okay? So that I definitely want to erase that. Not all of that. Just the red stuff. Okay, it's taking its time. We'll get there. I hope. Okay, it looks like we're almost there. There we go. So let's go back down to what we were working on before. Okay. So I just found the modulus, which was the length of the hypotenuse, by doing square root of 1 squared plus 2 squared. That's how easy that is. So the modulus was, the mod of z was equal to the square root of 1 squared plus 2 squared. That's why I was able to do it so fast, because it's really just very, very simple. And then to find the argument, that is the angle, I just said, all right, this is my a value, right? This 1 is my a value, and this 2 is my b value, and I know that the a value is the adjacent value, and the b value is the opposite value. And remember, tan, okay, inverse tangent is going to say opposite over adjacent. So I just plug the stuff in. So, well, that will be tan inverse of 2 over 1, which is just tan inverse 2, okay, or inverse tangent or arctangent of 2. And when I plug that into the calculator in degree mode, again, I got to say degree mode, or else it'll give you crazy answers in radians. Put it in degree mode, and you'll get the approximately 63.4 degrees. Okay, so that's the angle of rotation for this complex number. And I have a little note here. This took me less than 30 seconds on the TI-84. I'll teach you the tricks, but you must practice. So this is my big tip to anyone learning this. You should compute the modulus and the argument for every complex number problem you solve, because the more you do it, the more you'll understand it. The less you do it, the less you'll understand it. So we get better at what we do. You should be practicing this over and over again until it's second nature, until it's easy for you. And then I'm going to say you'll thank me later. Even if it's not required, you should do it as a practice. You will thank me. You will thank me later that you have practiced that to the point of being an expert at it, okay? Please, if you follow any advice in this video, please practice that. Now, subtracting complex numbers is just as easy as adding them. Instead of adding together the real and complex imaginary components of the complex number, you just subtract them from one another. So here's an example. Subtract 8 minus 3i from 12 minus 5i. Right? So be careful with the language there. I said subtract 8 minus 3i from 12 minus 5i. So we would group those real components together, 12 minus 8, and then add in the imaginary components, negative 5 minus 3i. And that works out to 12 minus 8 is 4, negative 5 minus 3 is a negative number, negative 8i, so 4 minus 8i. And when you do the modulus and the argument of that, those are the numbers you get here. Okay. Now we're going to move on to multiplication and division, and then we'll be done. So we already saw how to do multiplication. You use FOIL, okay? And just remember that I squared is negative 1. I times I, remember we're rotating twice, so I squared is negative 1. You have to remember that. So here's an example. 2 minus 3i times 3 plus 4i. We'll just do FOIL, first, outer, inner, last. You know, if you want to cover up the screen, pause it, write that problem down, and then you try to do it to make sure that you know what you're doing with your FOIL. First, outer, inner, last. You can also use box. Box works as well. So I'll show box here just since I didn't show it anywhere else. So that's 2 and then negative 3i. And then over here we've got 3 and 4i. So a lot of people prefer box. You know, I like FOIL because it takes up less space and I can just keep writing. But here's how you do box. You fill in these boxes by multiplying. What's 2 times 3? 6. What's 2 times 4i? 8i. What's negative 3i times 3? Negative 9i. What's negative 3i times pardon me. Negative 3i times 4i. Well, negative 12i squared. All right, so that's exactly what we did here. 6 plus 8i minus 9i minus 12i squared. So whether you choose to use box method or the FOIL method, I recommend FOIL because that is going to be the cleaner method to use. But please use box if that's more comfortable for you. I would just say that you're going to have to get comfortable with FOIL at some point, and some teachers may even require that you do FOIL just to prove that you can do it. It's actually easier because you can do FOIL in your head, where the box method kind of requires that you do this stuff on paper. Okay, so let's work this out. 2 times 3, 2 times 4i, negative 3i times 3, negative 3i times 4i all works out. Combine like terms. Okay, so I combine the 8i and the negative 9i. I got